What if humans discovered electricity before combustion? Close your eyes and imagine the world you know. Factories, trains, cars, planes, all of them born from fire, from burning wood, coal, oil, gas. Combustion built civilization. But what if we skipped that step entirely? What if, instead of taming fire to boil water and turn wheels, humanity stumbled onto something cleaner, quieter, and infinitely stranger? What if we discovered electricity first? Not in 1800, not with Volta's battery or Franklin's kite, but in 1200, in the age of castles and crossbows, before the steam engine, before gunpowder, before we ever thought to burn anything for power. Today, we're exploring a world that never choked on coal smoke, a world that never drilled for oil, a world where the Industrial Revolution was silent. And we'll see if that makes it better or just differently broken. 1247, the discovery at Baghdad. Our timeline splits in the House of Wisdom in Baghdad, or what's left of it after the Mongol invasions. A Persian scholar named Nasir al-Din al-Tusi, already famous for his work in astronomy and mathematics, is experimenting with amber and lodestones. He's trying to understand al-Karaba, the strange force that makes rubbed amber attract feathers. But he goes further. He wraps copper wire around an iron core. He spins a magnetized wheel near the coil, and he sees something no one has ever seen before. A spark. Not from friction, not from flint, from motion and metal. He's just built the world's first primitive dynamo. He doesn't understand electromagnetism. Maxwell's equations are 6 centuries away. But he understands this. Movement can create invisible power. Power that flows through wires. Power that can be stored, transferred, and used at a distance. And unlike fire, it doesn't burn anything. Why this matters? Why does this work here in 1247 when it didn't in real history? Because al-Tusi had the tools, the knowledge, and the intellectual environment, briefly, before Baghdad's libraries were destroyed. In our timeline, that knowledge was scattered. In this one, he writes it down. He demonstrates it to scholars fleeing the Mongols, and the idea spreads, not as science, but as alchemy, as mystery, as the closest thing to magic humanity has ever touched. By 1300, crude batteries, stacked copper and zinc plates soaked in vinegar, are being built in Cairo, Venice, and Constantinople. They're weak, inefficient, but they work. And humanity never looks back at fire the same way again. 1300 to 1500, the Electric Guilds. In this timeline, there is no coal-powered industrial revolution. Instead, there's something stranger, the rise of the Electric Guilds, secretive workshops in medieval cities where craftsmen build increasingly efficient batteries, coils, and primitive motors. They don't understand the physics. They just know that if you spin a magnet fast enough near copper wire, you get power. And if you run that power through another coil, you get motion. By 1400, water wheels along European rivers aren't grinding grain, they're spinning dynamos. The power is stored in vast battery banks, rooms filled with clay jars of acid and metal plates. It's dangerous, toxic, inefficient, But hey, at least it doesn't create smoke. The cost: no combustion, no gunpowder. Here's the first major butterfly effect. Without centuries of burning things to understand heat and pressure, humanity never stumbles onto gunpowder the same way. In our timeline, gunpowder was discovered in China around 850 AD through alchemical experiments with sulfur, charcoal, and saltpeter, all related to fire and combustion. In this timeline, alchemy pivots toward electricity. The obsession is with metals, fluids, and currents, not with explosive reactions. So cannons? Muskets? Rifles? They either don't exist or arrive centuries late, developed independently through different means. Wars are still fought with swords, crossbows, and siege engines well into the 1600s. Empires rise and fall slower. Colonization is harder. The world stays more fragmented because without guns, power is less centralized. And without coal, there are no steam engines, no locomotives, no industrial cities belching smoke. So what replaces them? This is where the timeline fractures into two worlds. Both start with the same discovery in 1247. Both skip combustion, but one leads to a cleaner, quieter modernity, and the other leads to stagnation, starvation, and a darker kind of industrial nightmare. Let's see both. The good ending. Scenario A, the silent revolution. In this world, the breakthrough comes in 1687, the same year Newton publishes Principia Mathematica in our timeline. But here, instead of just explaining gravity, the scientific revolution pivots toward understanding al-Kahraba. European and Ottoman scientists begin systematically studying electrical forces. By 1750, they've developed the first functional electric locomotives, not steam-powered, but driven by crude DC motors powered by massive dynamo stations along rail lines. Imagine it. Trains that glide silently through the countryside. No coal, no soot, just the hum of copper and iron. Cities don't become smoking hellscapes. London in 1850 has clean air. The Industrial Revolution still happens, but it's quiet. Factories are powered by rivers and windmills spinning dynamos. Workers still suffer, capitalism still grinds, but they're not choking on coal dust. By 1900, this world has leapfrogged into a bizarre kind of retro-futurism. Electric cars dominate, because internal combustion engines were never developed. Aviation is delayed by decades because electric motors are too heavy for early flight. But something interesting happens. Without cheap oil, without combustion, this world invests heavily in battery technology from the very beginning. By 1950, they've developed lithium-based batteries, something we didn't achieve until the 1990s. By 2000, their electric grid is entirely renewable: hydroelectric, wind, geothermal, and early solar. There's no climate crisis, no oil wars, no OPEC, no Exxon. The 20th century isn't defined by fossil fuels. It's defined by the race to build better dynamos, better batteries, better grids. The cost. But this world isn't utopia. It's slower, less explosive. Without combustion, chemical engineering develops late. Plastics don't exist until the 1950s. Pharmaceuticals are delayed. Airplanes don't dominate until the 1970s, when lightweight batteries finally make electric flight viable. And here's the uncomfortable truth. This world is more stable. which means empires last longer. Without gunpowder and oil to fuel rapid conquest, colonialism is less brutal but more entrenched. Monarchies persist. Social revolutions come slower. Is a cleaner world worth a less dynamic one? The bad ending. Scenario B, the Battery Dark Age. 1300 to 1600. The stagnation. But here's the other path. The darker one. What if electricity isn't enough? What if, without combustion, humanity doesn't get the energy density it needs to industrialize at all? Because here's the thing. Early batteries were terrible. A room full of acid-filled jars could barely power a single light bulb. Water wheels could spin dynamos, sure, but only near rivers. Wind power was inconsistent. In this timeline, the electric guilds hoard their knowledge. They become the most powerful institutions in Europe, but they can't scale. Electricity remains expensive, dangerous, and rare. So while a few cities, Venice, Amsterdam, Baghdad, glow with electric streetlights by 1500, the rest of the world stays dark, agrarian, stagnant. And then the competition begins. Without coal or oil, the bottleneck is metal, copper, zinc, lead. The materials needed to build batteries, wires, and dynamos. And there's not enough of it. Nations go to war over copper mines. Trade routes for zinc become as valuable as spice routes. The Ottoman Empire controls the richest deposits and becomes an electric superpower, while Europe fractures into petty kingdoms fighting over scraps. Slavery doesn't end. It shifts. Instead of cotton plantations, enslaved people are forced into toxic battery factories, handling sulfuric acid and lead. The electric guilds become corporate states, more powerful than kings. And the environment? It's not cleaner. It's just poisoned differently. Rivers run yellow with acid waste. Forests are stripped for copper smelting. The air doesn't have coal smoke, but the water is undrinkable. By 1900, this world has hit a wall. They have electricity, but not enough. They have motors, but not powerful enough. They have lights, but only for the rich. There's no plastics revolution, no aviation, no antibiotics, no green revolution. Population growth stalls at 2 billion because agriculture never mechanizes. And then, around 1950, someone rediscovers combustion. Not as a power source, they're too invested in electricity for that, but as a weapon. The first combustion bombs are crude. Liquid fuels ignited in enclosed spaces, but they're devastating. And suddenly, the world that skipped gunpowder gets introduced to chemical warfare in its rawest, most brutal form. This is the world where skipping fire didn't save us. It just delayed the burning. So which world do we get? The one where electricity gives us a cleaner, quieter industrial revolution? Or the one where skipping combustion traps us in permanent scarcity? Here's what haunts me. Both timelines are plausible. The difference isn't the technology. It's whether humanity can scale that technology fast enough to avoid collapse. Because combustion wasn't just brutal, it was dense. A lump of coal contains more energy than a room full of medieval batteries. Oil could be shipped anywhere. Gasoline could power engines small enough to fit in cars and planes. Electricity is cleaner, but it's harder. And maybe that's the trade-off. A world that doesn't choke on smoke, but takes twice as long to reach modernity. Or a world that never reaches it at all. Maybe the real question isn't whether we could have discovered electricity first. Maybe it's whether we were supposed to struggle through fire first, to learn the cost of burning things before we earned the right to move past it. And if we'd skipped that lesson, would we have built something better or just broken in a different way?